All right, good afternoon, and welcome to the first official monthly research webinar we're having here in TRANS-IPIC, the Transportation Infrastructure Precast Innovation Center. It's my pleasure to be with you here this afternoon. Those who don't know me, my name is Bassem Andrawes, and I'm the director of TRANS-IPIC. This is, as I said, our first monthly webinar. We're starting this series of webinars where we basically will be having a monthly webinar with two of the research groups who are working with TRANS-IPIC will start actually sharing their research findings with the rest of the center. And as you probably have been noted before you enter here, is that this meeting is being recorded. The purpose of that is basically that we are going to be sharing these presentations with the community, and that will help us disseminate the knowledge that we create through the center, as well as exchange ideas with the rest of the world. So that's the whole point of these webinars. Very exciting. We have two groups today who are presenting, one from the University of Illinois and the other from Purdue University. So we're very excited to have them with us today here. The webinar shouldn't take more than an hour or so, about 25 minutes or so for each group, including questions. It's pretty interactive. The whole point of it is that the rest of the center affiliates and researchers get to observe and comment on the rest of the group's work, and maybe that will promote the collaboration, future collaborations, and new ideas within TRANS-IPIC. So just as Chris showed here in this slide showing the next webinar we are going to have is scheduled already. You haven't been maybe informed about it, but here's what we are going to do about it so far is that it has been scheduled for March 4th, 2 to 3. We found apparently that this time works for the majority of the researchers, Monday on 2 to 3 p.m. We know that that could vary, and we are flexible in scheduling future webinars depending on the availability of the researchers. But for the next one, we are expecting it to be March 4th, and you will be receiving a notification about that soon from the center management team. Also, another exciting thing I want to share with you is, or remind you, hopefully all of you are aware of that already, is the upcoming workshop. Our first workshop for TRANS-IPIC, that's going to be in person, of course, and that is going to be held in the Chicago area in Rosemont, Illinois. That's about like 10 minutes from O'Hare Airport, so it's very convenient. And the location is very exciting and very vibrant. So I really encourage you all to plan ahead of time to attend this exciting workshop where we all get to share. First of all, get to see each other in person. That's a very exciting thing. I don't think all of us got the opportunity to meet in person, but that would be a great opportunity for us to meet and to discuss our research findings and to see how we can even push our center to next level. So that's going to be April 22nd. It's a one-day event, and we have sent you the registration link. So I would encourage you all to register because the spots are very limited, and we're running out of room very quickly. Especially that we're expecting also our industry partners to join us in this event. So it's not only for the researchers, but also for the research, the center affiliates from the industry and the community. And with Chicago being the place where this is held, we're expecting this to attract some attention there. So without any further delay, I would like to introduce our first speaker for the webinar today, Mr. Siyoung Park. And he's one of my PhD students. He's working under my supervision. And Siyoung joined the University of Illinois in the fall of 2022. And he is a member of the Shape Memory and Structures group. His research interests and the field is in the area of bridge engineering and the application of smart and advanced materials in infrastructure. The title of his presentation today is Shape Memory Alloy Transverse Reinforcement for Solving End Region Problems in Precast Bridge Girders. This is one of the projects that is funded by TRANS-IPIC. I think it was last fall when we started this project. So with that said, I would like to have maybe the mic pass to Siyoung. Siyoung, go ahead, please.
Thank you, Professor, for your introduction, and nice to meet you, everyone. Thanks for coming to the first TRANS-IPIC webinar. I'm Siyoung Park, a PhD student in University of Illinois at Urbana-Champaign. My research topic is shape memory alloy transverse reinforcement for serving end region problems in precast concrete girders. This work was done with my advisor, Professor Andrawes, with support from TRANS-IPIC and UTC. Prestressed concrete girders, especially pre-tension girders, are used in diverse large-scale infrastructures, including parking lots and bridges. Nowadays, to economically and safely build these long and large structures, I-shaped and bulky girders with large flanges and narrow webs are manufactured. We can see in H2 girder design guideline that Type 5 girder is designed with 42 and 28 inches width flanges, whereas web has 8 inches width. So by constructing girders with large width and narrow span with using numerous strands, concerns about pre-stress release is emerging in pre-tension concrete fields. Uchi in 1983 suggested a stress model for pre-stress release. Bursting stress, spalling stress, and splitting stress are those that are developed near end region, which induce cracks. To overcome this, H2LRFT specified requirements for vertical reinforcements and confinement reinforcements. It is highlighted that stress in steel within length of height divided by 4 be less than 20 KSI. However, even with securing this specification, we can still see inclined and horizontal cracks in end region of pre-stressed girders. Several studies were conducted to mitigate the end region cracking. Following 4 methods were developed as a solution. First is to adjust draping angle, and second is debonding strands with partial shielding, such as an unbonded strand. Both methods showed some effect on end region, but by up to 20% less damage, but there was a reduction in shear capacity when conducting 2-point load experiments. Third is vertically post-tensioning, and fourth is vertically using threaded rods. These methods also presented some effect on crack mitigation. However, extra steel components or bulky rods were required, resulting in steel congestion, especially in end region. In this study, active confinement effect of SMA as a pre-stressing force was used for crack mitigation. It was thought that replacing steel stirrups to SMA stirrups can relieve crack damage by confining force and even reducing steel congestion by using a smaller number of end region stirrups with larger spacing. Nickel titanium niobium SMA alloy type was used for numerical analysis, which has wide range of thermal hysteresis, resulting beneficial effect on application in civil engineering field. Thermal pre-stressing is done by using shape memory effect of SMA. This is SMA tries to recover its original shape when heated up beyond austenite temperature. Using this feature as shown in the animation, we pre-strain the SMA and anchor it. After that, by heating with direct heating or electric method, as the SMA is fixed to the anchor, it cannot recover to its original shape and building recovery stress. This confining or pre-stressing force would be transferred to concrete, limiting cracks. Usually, direct heating is done by torch heating or placing in heating chamber, and electric activation is done by applying low voltage activation. Among diverse SMA types, nickel titanium niobium SMA was selected for the analysis. Nickel titanium niobium is composed of reversible particles nickel titanium and irreversible niobium. This is that when the SMA is deformed and heated up, nickel titanium particles begins to recover, whereas niobium hinders its recovery. This reaction widens the width of thermal hysteresis, making ambient temperature to be upper than the martensite start temperature. While thermal hysteresis would maintain the recovery stress even in ambient temperature or below minus 70 degrees Fahrenheit, being capable for use in diverse applications. With these features of SMA, it is already used in diverse engineering fields, including aerospace, robotics, cardiovascular science, and mechanical engineering fields. Representative applications are in airplane engine components, SMA actuators, and pumps, and also artificial heart devices. Before applying SMAs, to verify the numerical model, BT72 girder bridge model was designed based on PCI bridge design manual. The length of the bridge was designed as 120 feet with end stirrups up to 18 inches, 36 straight pre-stressing strands and 12 straight pre-stressing strands were designed with 7 wire strands in a diameter of 0.5 inches with applying pre-stress of 202.5 KSI. All these stirrups and confinement reinforcement satisfy the recommendation of AASHTO LRFD specification. Finalized numerical model is shown in the figure. Element types of concrete was designed as C3D8, which is 8-node linear brick element. As the numerical analysis was focused on the end region, denser mesh was defined with size of 2 inches, but increasing to 4 inches after 120 inches from the end face. Compressive and tensile stress strain curve was designed as shown in the graph, following the Hockness-Dip parabola and ACI code. Compressive strength of the concrete was set as 5.8 KSI based on PCI bridge design manual, and tensile strength was calculated following the ACI code. All steel components were specified as T3D2, which is 2-node linear truss element type, and yield strength of rebar was defined as 50 KSI, and pre-stressed strands were designed to be 7-strand wire strands with ultimate strength of 270 KSI. Now, to evaluate the damage on BT72 girder, the maximum principal strain of the end region was analyzed after pre-stress release. Red areas are those which are thought to be fully cracked. This was set based on the value of twice of the cracking strain, which was calculated also based on the ACI. As the pre-stress level increased, we can see that crack regions are developing in web and flange areas. When the pre-stress level was 101.3 KSI, there were only minor cracks in the surface of web and flange areas. Still, we can see that web-flange connection part was most damaged, and the shape of the crack was in Y and horizontal. As the pre-stress release level went up to 151.9 KSI, inclined crack at top web also appeared, which is evaluated to appear by the draped pre-stressing strands. Bottom flange was almost fully cracked in end region where horizontal pre-stressing strands are running through and web splitting cracks also developed. At the end face with pre-stress of 202.5 KSI, the web region was cracked more than 50% with vivid cracking pattern of inclined, web splitting, and Y shape. Although this numerical model followed the AASHTO guideline, we can still see that end region cracking can be a problem. Also, by comparing to the field test, although the model is not the same, the cracking pattern was similar, verifying the numerical model. The stress distribution along the vertical reinforcements at end regions was also evaluated to see if BT72 girder satisfied AASHTO guideline. Although the bursting resistance was satisfied with showing 2.1%, which the code is saying 4%, the outermost startup exceeded the value in the middle and bottom of the girder with values of 23.8, 24.1, and 20.2 KSI. However, after that, the stress diminished quickly, and after third startup, the stress reached below 10 KSI. We can see that most stresses are distributed within third layer, implying that these regions are really vulnerable to cracks. As a result, SMAs were replaced within third layer in further analysis. Now, to start with SMA model, whereas steel startups were designed in U-shape, SMA startups were designed in L-shape to mitigate stress concentration by pre-stress at the bottom flange. 3 types of SMA models were designed with changing 5 end startups. 5S2, 5S1, and 3S1 are cases with SMA startups. 5S2 had 5 end startups with 2 SMA startups at the end region, and the volume ratio was 1.66%. 5S1 also had 5 end startups, but with only a single SMA startup. The volume ratio was 1.65%. And lastly, 3S1 had 3 end startups with only 1 SMA startup with volume ratio of 1.0%. We can see that from 5S2 to 3S1, the volume ratio is decreasing with less amount of end startups. To graphically see this, in case of 5S2, 2 SMA startups were replaced to mitigate the crack damage shown in BT72 case. After that, the number of SMA startup was reduced to 1 to also see the effect with a smaller number of SMA. Actually, it would be best if we can replace small number of SMA with sufficiently relieving damage. After that, the number of end region startups was reduced to 3 with 1 SMA startup. This was to reduce steel condition while limiting crack propagation. In total, original steel case to 3 SMA cases were compared in terms of cracked area, cracked width, principal strain, and stress distribution in end startups. The effect of SMA was analyzed in terms of cracked area at the web region. Most of the pre-stressing effect was with horizontal cracks, and there was slight effect with inclined cracks. By calculating the cracked elements, the original BT72 model had 54.2% of cracked area, whereas each SMA model had 23.7, 33.3, and 33.4% of cracked areas. Placing 2 SMA startups had the best effect, but with a single SMA, it was also effective. If we observe on the web center region only, most of the horizontal cracks were diminished by even applying just 1 single SMA startup. Even with larger spacing of 8 inches, this was similar. It can be thought that the difference of cracked area of 23.7% to 33.3% was in inclined cracked area, and since there was no difference between 5S1 and 3S1, it was promising that SMA could truly relieve both crack propagation and steel congestion. Now to compare the crack width in each models, at the surface of BT72, the crack width exceeded 0.007 inches until approximately 0.75 inches. In ACI 224R, it recommends crack width to be below 0.007 inches to resist design chemicals in reinforced concrete under service loads. As generally, clear cover of reinforced concrete, and also for this model, is taken as 0.5 inches to 0.75 inches, this could bring negative influence to girders by steel corrosion. However, with replacing SMAs, the crack width reduced to below 0.005 inches at the surface, and after passing SMA startup at a distance of 2 inches, it was nearly sealed. With analyzing cracked area and crack width, we could find that applying SMA in pre-tension girder could prevent extensive cracking and improve serviceability. The effect of SMA was also shown in the relationship between principal strain and pre-stress value. The maximum principal strain at the center of the web reduced 90%, explaining why there was negligible cracks in the prior figure. Also, at the bottom of the web, in web flange connection, principal strain decreased 20%, depending on the number of SMAs and end startups. 5S1 and 5S2 experienced 40% reduction in principal strain, and even in 3S1, 20% was reduced. With this result, although inclined crack mitigation was slightly shown visually, we can quantitatively evaluate the effect of SMA to crack propagation. Finally, by inspecting stress distribution and variation within end stirrups, the variation of stresses with SMA models were mostly below 10 KSI. The maximum stress variation was at 3S1 case with 10.4 KSI due to its large spacing of 8 inches. Still, the value was under 20 KSI and even lower than stress generated in BT72 model in equal locations. As per to H2 codes, the demand of stirrups at the end region can be reduced with using SMA stirrups. Now is the ongoing experimental program that we are working on. To validate the effect of SMA bars at end regions, scaled down H2 type 1 I-beam was set as a reference model, placing a single pre-stressing strand at the web region. Web width was designed to be in 3 inches, and pre-stress value was also set as 202.5 KSI. By comparing steel and SMA startup models, we are expecting crack mitigation and possibly future load tests can be done. Preliminary numerical analysis was performed in the scaled-down model as seen in the figures. Focusing on the crack at the web, we could see significant effect of crack mitigation in length and width by applying only 2 SMA stirrups at the end region. By referring to the results, the SMA effect was proven, and we are now in progress for experiments with diversifying variables such as number of SMA stirrups, SMA activation method, and the location of SMA stirrups. The thermomechanical characteristics of nickel titanium niobium SMA is also under investigation. As SMA has different attributes by temperature, a monotonic and cyclic testing are in progress. There was a previous study of nickel titanium niobium SMA wire in austenite phase in terms of pre-straining and activating. Now we are focusing on the martensite phase to early activation from martensite phase to austenite phase. Activation method, temperature, and pre-strain value can be a variable for determining the recovery stress, which should have an effect on the concrete, so these studies are going on. To summarize, replacing steel stirrups with nickel titanium niobium SMA stirrup reduced crack area in web by up to 55%. Horizontal cracks were mostly eliminated by pre-stress force of SMA stirrups. Single SMA stirrup also showed effect on crack mitigation with alleviating steel congestion issues. 20 to 40% of maximum principal strain reduced by SMA stirrups. Crack width was limited under 0.007 inches by SMA stirrups, and experiments will be done to verify the numerical analysis results and investigate the thermomechanical characteristics of nickel titanium niobium SMA. Authors would like to acknowledge the financial support provided for this research from Transportation Infrastructure Precast Innovation Center through the U.S. Department of Transportation University Transportation Center program. Thank you very much, and please give me any questions.
Thank you, Siyoung. Now we have a few minutes for questions or comments for Siyoung. Anyone with question can take the mic and go ahead and.
May I ask a question? Hi, Siyoung. This is Pinar from University at Buffalo.
Yep.
So how does the stiffness of the SMA bar compare to steel? And then also, are you pre-stressing these in the end regions? That part I didn't catch.
Okay, first of all, the stiffness would be kind of similar to steel and SMA.
Okay.
And we are actually pre-straining almost from end to end using a special testing bed. Mm-hmm. And I think maybe that'll be presented at the next, at the Rosemont session. So you might can see that.
Okay.
Yeah.
And is that like a heat-based pre-stressing then?
No, it is by just mechanically pre-stressing.
Oh, I see. Okay. So in that case, sorry.
The question, let me, because I'm working with Siyoung with this Pinar. You are referring to the pre-stressing of the steel or the SMA, Pinar?
SMA.
Okay, Siyoung, I think Professor Okomos is referring to the pre-stressing of the SMA.
Oh, okay.
So you can maybe clarify that, how the pre-stressing is done?
Okay, so first I need to pre-strain the SMA. So it is usually taken from 10 to 15%. And then I could anchor it using an anchor chuck. And then I activated it using electric method, or also heat chamber or other methods can be also used. And as the SMA is anchored to the end tips, the pre-stress value, the pre-stressing force is generated.
Okay,
But
so I guess
if
where I was going with this is that if it's heat-based and if there is, because there's going to be curing and they do steam curing, so when the temperatures rise, do you expect the change? Is my main question.
I believe that the activation temperature should be over 100 degrees Celsius. So there might not be that much effect on the SMA, but now I'm trying to activate it inside the concrete. So that would be also a good point for me to study about. Thanks for your comment.
Yeah, thank you.
Any other questions or comments?
Okay.
Yeah, one of the, let me just add to this, clarify. The good thing about the shape memory alloys is that they can reach the target temperature, which is, as Siyoung said, at 120 degrees Celsius in a matter of 2 seconds. And we have tried different methods to do that, including using induction heating, which is very effective. And we have another project we're going to be talking about in the workshop related to induction heating also that shows the efficacy of such technique. But the method that Siyoung was referring to is related to electrical heating. So again, it'd be very interesting to present maybe to you next time these methods of heating and how they can really bring the pre-stressing to a very high level in a very short period of time that would not impact the concrete based on our studies. Okay, any other comments or questions to Siyoung? Okay. Well, thank you so much, Siyoung. Now we can move to the next speaker. Our next speaker is from the Alliance School of Civil Engineering, Mr. Zurui Hong. And Mr. Hong is a PhD student working under the supervision of Professor Hubo Kai at Purdue University. The research interests of Mr. Hong include human-robot collaboration and communication. So, Mr. Hong, please go ahead and share your screen if you want to.
Sure. Professor, can you hear my voice?
Yes, I can hear your voice clearly.
Great. Let me share my screen. Can you see my screen?
Yes.
Great. So let's get started. Good afternoon, everybody. Welcome to my presentation. My name is Zurui Hong, and I'm a PhD student in civil engineering at Purdue University. The topic of my presentation today is a BIM-based framework for holistic quality control in precast concrete construction. And this project is conducted by the PIs, my cohort, and me. In my today's presentation, I'm going to focus on 3 main points. First, I will give an introduction of this research project, and then I will talk about the research methodologies and our implementations in the project. And then we'll end the presentation by discussing a few findings today we have of the project. So the precast concrete systems, which we call PCS in short, has been widely used by the US DOT agencies to build the transportation infrastructure and address the related challenges. And PCS can provide many benefits as an alternative to cast-in-place concrete systems. Among the list, the example can include, for example, minimize traffic disruption, a shorter project duration, and so on and so forth. However, the defects that occur in any project life cycle stage can offset the mentioned cost and time savings. And the current quality management practice, the QM practice, are limited in dealing with those potential defects in mainly two aspects. First, the current practice is isolated within each lifecycle stage. The data loss can happen when the project moves to the next stage. And the second is the current practice heavily relies on labor-intensive and sporadic inspections, which could be possible to meet important quality problems. Here are a few examples of those quality concerns. For example, we could have insufficient concrete covers to protect the rebar from the corrosion. We could have missing rebars during reinforcement placement. We can have unidentified chipping defects of the concrete, the PC elements. So all of these undetected quality problems can either degrade the durability of the structure or delay the project caused by the extra times needed for the defects repairing. So the limitation of the current QM practice reveals a critical need for a holistic quality management for PCS from a life cycle perspective. And the BIM is considered as a solution for this holistic PCS QM. As we all know that the building information modeling is a promising technology to facilitate the information communication. As we can see in this figure 3, the traditional quality management practice can experience the data loss during the project stage transitioning, and the BIM can address the problem with its standard storage of the data and a seamless exchange of the information or knowledge. And with the progression of the project, it can enable a continuous accumulation of the quality knowledge for the quality management decision making. However, we should know that BIM only works as a data communication hub, but doesn't take care of the data collection part. So that is the place where the sensing technologies come into play. Using sensing technologies such as the laser scanner and the ground penetrating radar can automate the laborious inspection tasks, which could reduce the possibility of missing those quality problems. And also it can help improve the worker safeties by not exposing the workers to the physical hazards. By combining BIM and sensing technologies, the idea of scan to BIM can let us achieve a live digital twin of the transportation infrastructure for intelligent and effective quality management. So taking laser scanner as an example, we can use the laser scanner to collect the 3D point cloud data of the forms and the rebar mats, and we can use algorithms to extract the dimensional data of these elements to analysis its dimensional tolerance, and we can store this data to an up-to-date BIM model as a digital twin for the PCS QM. So based on this given background, our overarching goal of this project is to develop, validate, and test a holistic quality management framework as a model for precast construction of transportation infrastructure. As you can see in this figure 5, we can utilize BIM sensing technologies and deep learning algorithms to generate a live digital twin of the infrastructure for a continuous monitoring of the quality. And to achieve the goal, we break down the goal into 2 objectives. We first design a system level framework for lifecycle QM of PCS, And second, we explore BIM for PCS in precast at plant stage. In this project, we establish a project advisory committee, which is composed of the people from NDOT, contractors, and precasters to help us disseminate the project findings into practice. And this slide shows an overview of our project work plan. So in task 1, we will design a system level framework for the lifecycle data acquisition and data exchange in PCS. In task 2, an expandable BIM approach is designed to meet the data information needs of lifecycle PCS QM. And we will validate the design framework and approach using a case study and which targets at the precast at plant stage. And we will also hold a panel discussion at 2024 Purdue Road School to exchange ideas, share project findings, and hear from the experienced researchers and practitioners in the field. In the next slides, I will show you guys more details about the task 1 and 2 and how we implement the task. So in task 1, we investigate and compare both the current practice of PCS QM and also the state of the art of BIM practice in PCS QM. So for the current practice, we focus on these critical aspects. For example, the timing of the QC/QA tasks, the involved stakeholders, the data collection methods they use, the tools, data needs, formats, and so on and so forth. And for the BIM practice, we focus on we look into how BIM changes the traditional work progress and data flow, as well as how we can integrate the sensing technologies into the workflow to improve the QM work. And then we compile all the knowledge into the two frameworks. So we have the baseline framework, which describes the workflow, the work process of the current practice. And then based on this baseline framework, we integrate BIM and sensing technologies and establish a dynamic system level framework for the digital twin system design. And let me show you more details about how this dynamic system level framework looks like. As you can see in this figure 7, it shows this dynamic system level framework and how it is characterized by the expandable BIM models with the development of the project. So we probably could have not too much quality information about a PC, columns at the production stage, but with the progression of the project, the level of the development of the BIM models get increased, and we could have more as-is information. For example, the physical damage status of the column come in and collected those data in the O&M stage. And in our project, we first target at how to establish a baseline framework. We take the precast concrete pavement system as an example and examine the latest manuals and specifications to compile the current practice knowledge. We organize those knowledge by following this breakdown structure. So for each life cycle stage, we identified the QC/QA tasks and what's the timing and the responsible parties. And then we look into the specific checklist and check items, and we organize those check items in a format of object attribute structure for the later BIM template design purpose. We also look into the data collection details for each check items. For example, what's the data type, data unit, and collection pools. And also to investigate the state-of-the-art of BIM practice, we comprehensively reviewed the existing sensing technologies used for the automated inspection task. We focus on the following important aspects to understand how BIM can change the traditional inspection workflow. For example, the sensors, the technology used, what's the money cost, and the application in the inspection, what's the tested environment, and the most important thing is the measurement accuracy of these sensing technologies. And there's an example, a graphical illustration of one of the sensing technologies, which is we can utilize the laser scanning to check the dimensional quality of the bridge deck panels. We can collect the 3D point cloud data of those panels on the field and compare it with the S-design models to conduct a dimensional deviation analysis and determine whether or if the dimensional tolerance is satisfied or not. In task 2, we focus on designing and expandable BIM templates using IFC. So IFC refers to Industry Foundation Classes, which is an open international standards to digitally communicate the data in our AEC industry. So our goal is to have a expandable IFC data model that can accumulate the quality data throughout the life cycle of the project. And during the design, we will assess the data needs and exchange to improve the design. And we will implement our design with the synthetic data in a desktop simulation, which involves the production operations at plant. So in our project, we aim to answer these 2 key research questions regarding the IFC representation. So the first one is how to extend the IFC data schema to describe diverse PCS-QM concepts. And second, how to define IFC data structure to document the quality management history and support the downstream analysis. And this slide explains how IFC can represent the inspection data. So IFC, as I mentioned, is an open international data standard, and it describes the concepts in an object-oriented manner. In other words, it uses the classes, relationships, and attributes to describe those concepts. So in IFC data schema, it has numerous built-in entities, the class entities, relationship entities, and attribute entities. And each entity has its own specific defined semantics for us to describe specific concepts. And we can find those information in the existing online IFC specifications. And let me give you an example to understand how we can represent a real-world inspection scenario using IFC. So for example, we could have an QC inspector conducting an inspection task for the post-fall checking of the PC elements at plant at a specific time. So after the inspection, he or she could find a few cracks on specific slabs. And the inspector has to record the properties of those cracks. For example, the properties can include the width, location, and severity, etc. And the inspection results needed to be summarized. And we will use the class-oriented object-oriented modeling to first model the defect inspection. So we could have a class called inspection task. The task has the time. The task also has the results and with its description. And in the results, we can find the detected crack elements, which could have multiple attributes like the width, length, and each crack element is founded on the specific slab, which has the ID of itself. And here is how IFC represents the same inspection data. So it also used a similar idea, but with the IFC entities, the schema defines. So we could also have the class to define those concepts. And here, the red color text means the concepts we want to describe. And we could have the task, IFC task, IFC element assembly, IFC slab, and so on and so forth. And these class entities are connected with the relationship entity. And each class entities also have some attributes. Those attributes themselves can also be the class entity. For example, the IFC task time. And we can also add our user-defined properties to describe the crack elements. For example, we can use the IFC property sets and the property single value to describe the attributes like the length, the repair action for these crack elements. And then we implement this example in a desktop simulation. We created IFC entities. Sorry, is there any questions from the audience? Okay. We create the IFC entities using the IFC OpenShare, Blender BIM, and Python. And we visualize those tested objects and attributes in another software called IFC Open Viewer. And here is the visualization results of those tested attributes. So we we create an object called crack elements 01 and attach it to the floor of the type generic 12 inches. And this slab has the ID, and the crack elements has many user-defined properties. For example, the crack properties, the location properties. And of course, there are some IFC entities we cannot visualize in the current commercialized software at this stage. So I show an example of the task, IFC task entities here. It is a record from the original IFC file. And you can tell how the IFC files describe IFC entities. It starts with entity ID and the entity itself, and a parenthesis that contains many attributes. For example, the global ID, name, status, data collection method tools, and so on and so forth. So that's the implementation of our project. In the last page of my presentation, I want to share some findings today we have. So first, we found that the IFC can be extended and customized to support the lifecycle QM of PCS. And second, a complete history of the quality management data that are integrated in IFC and BIM can lead to a semantic rich digital twins for PCS. And last but not least, in the precast at plant stage, non-buried sensing technologies automate the acquisition of dimension and surface quality data for the PC elements. And that's all the things I want to share with the audience. And thank you for your attention and listening. I will be happy to answer any questions if you have.
Thank you, Zurui.
Thank you.
Very good presentation. Really appreciate that. Time for questions.
I have a question.
Go ahead.
I have several questions. My first question, at the beginning, you were showing the maintenance part. The slab is deteriorated or the rods are deteriorated. You can either replace it or you can put a new one. Did you do any kind of economic analysis on that? That which process? Hello?
Thank you for the question. Please correct my understanding if I'm wrong. So you are asking if we have done any economical analysis using the this IF representation BIM templates. The answer is we haven't done that yet. So the project is still ongoing, and we are still testing the how we can better design those BIM templates for the downstream analysis you mentioned, like the cost estimate, economical analysis. So we haven't done that part yet.
Okay.
One different comment, Baba, before you continue, is if everyone could please mute themselves.
I can hear
only
well.
the person asking the question could unmute themselves, but everyone else who is not asking the question, I would ask them to please mute themselves.
Okay.
Thank you so much. Thank you. Go ahead. Keep going, Bob. Sorry for the interruption.
I should ask. That's what you mean?
Yes, go ahead, please. Keep going. Yeah.
My second question was regarding the measurement. If you take your experimental slab size is very small, and if you measure the dimension, the error will be very small, which sometimes may not be detected well. But if you take a large slab and measure that, then your error can be easily detected because it will be more visually visible. So in that case also the cost again comes. It will take a lot of money and time. So which one you will go for? If you have a very small one, that is susceptible to more error than the bigger slabs.
Oh, thank you for your comments. I think it's really valuable. So your comments is like if it worth to use the sensing technologies to detect those very tiny dimensional errors. Yes, that's very good. So first we will comprehensively investigate the current sensing technologies, and definitely the errors is impacted by the dimension of the elements we will monitor. And there are many technologies which can already achieve a pretty good performance in monitoring or measure those tiny errors. But we will also consider its economical cost. For example, if we use the laser scanner, we can definitely achieve a good performance, but it will cost maybe $70,000 or $80,000, which is not acceptable to the practitioners. So we will also consider that economical cost part. So do I answer your questions, Mr. Sekar?
Yes, that's what I was pointing out. Okay,
Thank you.
very much.
So can I chip in? So I think, the main purpose of investigating the sensing technologies is we don't specifically target at small errors or larger errors. Basically, we are more looking at how a technology can help with automating the task. So this is the main purpose. And the other part of the beautiful part of using sensing technologies is it can help us automate the quantification process. So when we do visual inspection, we might be able to tell that you have some larger discrepancies or some corners being knocked off, etc., etc. But being able to quantify to what extent the damage is can be very helpful, because that's also something we heard from the field practitioners regarding the many of the conflicts they face in the field when different sides arguing whether a precast element is replaceable, repairable, or can be used directly.
Mm-hmm. Okay, thanks.
All right, other question? Any other comments for Zurui or Professor Kai? Okay, well, thank you so much. Well, again, very excited that we had two excellent presentations today, and I like the questions so much because that's the whole point of having these webinars, is to create some kind of interaction and, you know, maybe triggering maybe new ideas and new directions of research. Our center is a very diverse center when it comes to precast concrete. Yes, we might say it's only precast concrete, but when you look into the projects, which is about 18 projects funded so far by TRANS-IPIC just in the first year, they're all very diverse in how they tackle the issue of durability and extending the life of transportation systems, precast systems in particular. So it's very exciting to see more of this work in the future. I'm really looking forward to our next webinar, which, as I announced earlier today, it's going to be March 4th. So please mark your calendars. We're going to have two other excellent presentations on March 4th. In addition to, again, the workshop, which will be held on April 22nd, where we can all meet in person and, you know, get to know each other a little bit more better. We're just starting the journey of TRANS-IPIC the first year, and we're looking forward to more you know, collaborations and working together over the next 4 or 5 years. Please feel free to reach out anytime to either me or Chris, who is with us today, the project manager, who is doing a fantastic job trying to help everybody in the center. So if you have any questions or have any comments, please do not hesitate to reach out to any of us. Thank you all. Any final comments or questions before we wrap it up? Okay, thank you all. It was a pleasure, and until we see you next time. Thank you. Bye-bye.
Thank you.
Thank you.
Everyone.